this is Mrs. Facca here giving you a lesson on Hess's Law. So as you know in this chapter on enthalpy, it's kind of like if you ever watch, if you're like me and like to watch recipe shows, maybe someone at home does if you don't watch them. Sometimes they'll do like chicken 3 ways. Well, this is kind of like chicken 3 ways. We will be calculating in these next kind of mini videos enthalpy, not 1 way, not 2 ways, not 3 ways, 4 ways we're going to calculate enthalpy. And that's really the crux of this chapter, chapter 5. So the 4 ways in which we are going to be able to calculate enthalpy. The first is Hess's Law, which we're going to do today. Then we're going to do delta H naught F, the enthalpy of formation, then bond energy, and then I think Ms. Schuhart's going to tag in for number 4, calorimetry. So it's like chicken parmigiana, grilled chicken breast on a bun, chicken barbecued chicken, and the last one is chicken burgers. So you've got 4 different ways to calculate enthalpy, chicken 4 ways, enthalpy 4 ways. Here we go. So today we're going to be doing Hess's Law. I think I could have come up with more chicken recipes than that. So this is Hess's Law. And with Hess's Law, you're going to be given a target reaction. And as I illustrate how we work through a Hess's Law problem, you're going to see some of the beauty and magic of thermochemical equations. So here is our target reaction. All right, we've got solid carbon combines with water in the form of steam to yield carbon monoxide and hydrogen gas. Now, it's not the case for this particular reaction, but there may be a reason why you cannot conduct a particular chemical experiment to determine its enthalpy directly experimentally. Maybe the reaction is too dangerous to carry out in a laboratory setting. Maybe you don't have all the reagents that you need. That's when Hess's Law really is going to help you out. Because if you want to calculate the enthalpy of this reaction, but you can't actually carry it out and you don't know what the enthalpy of that reaction is, we can look at a series of elementary steps that add up to our target reaction. That's the beauty of Hess's Law. If we want to calculate the enthalpy of the target reaction, we can utilize the series of elementary steps to get to our target reaction. So what that involves doing is manipulating these elementary steps. Typically there's 3 steps. Sometimes there's 2, there can be even more than 3, but usually we keep it to about 3. So what we want to do is we want to manipulate each of these steps, each of these reactions, such that we end up, when we add up these steps, we end up with the target reaction. So I'll share with you kind of my thinking process. So in step 1 here, I have a look and I think, okay, great. I've got carbon on the reactant side here, and my target reaction has carbon on the reactant side. So I feel pretty good about the fact that carbon's on my reactant side, and the coefficient is 1 in both cases, because that's what I'm trying to get to. The important thing to do when you're manipulating these steps is to make note of what you're doing, because odds are the first time you do it, you're not going to do it correctly, and then you're going to have to go back and maybe undo something. So I've numbered the reactions 1, 2, and 3. So I'm going to make a note to myself of what I'm doing to reaction 1. I'm just going to say I'm multiplying it by 1, which means I'm essentially leaving it alone. I'm not reversing the reaction. I'm going to omit subscripts just for the sake of time. And we also want to include our enthalpy term. Okay, so first reaction. In the second reaction, I've got carbon monoxide and oxygen, and I've got carbon dioxide. Well, when I'm comparing it to my target reaction, I'm like, well, carbon monoxide's on my product side. So I want to get, more than likely, this carbon monoxide to my product side. So what we need to do, and that's the beauty of thermochemical equations, is if we reverse a chemical reaction, all we have to do is reverse the sign on the delta H. It's like if you walk home forwards today, and then tomorrow you walk home backwards, you're not doing it quite the same way, but it's still the same amount of energy, just opposite. So what I'm gonna do to reaction number 2 is multiply it by -1. Okay? Again, we don't know if this is right. I kind of do though, that it is, but you know that you can always fix things if you need to. So we're going to make our products our reactants and our reactants our products. And I like for the arrows to line up because it's much easier when you're adding up the chemical reactions at the end. 1/2 O2. And so because we reversed the chemical reaction, we're also going to reverse our enthalpy term. So we've gone from an exothermic reaction that has a negative sign that now is an endothermic reaction. All right, so our last reaction, we have our oxygen and hydrogen as our reactants, and right away I think, man, I'd like that hydrogen on the product side. We've got water on the product side, I want it on the reactant side, so I feel pretty good about multiplying reaction 3 by -1 as well. So again, we flipped our reactants and products, and we're also going to flip the sign of the enthalpy term. So our delta H is now, and actually I like to include the positive in front because then I know it's a positive and I just didn't forget my negative. Because I know this is simple math, but it's really easy to just make a mistake by forgetting to write in a sign or make assumptions, because it's just a silly way to make a mistake in your final answer. So by adding that positive there, it tells me, okay, it is positive and not just that I forgot the negative. So the delta H in this case is going to be positive 242 kilojoules per mole. So let's see if we did this correctly. So now we add up our steps, and we can cross out anything that appears on the reactant side in one equation and on the product side in another equation. So here's carbon dioxide, it can be canceled. And for example, if I had a coefficient of 2 here, well, I could only cancel out one of those because I only have 1 on the product side. If I had 2 on the reactant side, I would still be left with 1 on the reactant side. But in this case, both coefficients are 1, so I can cross out my reactant, my product. Let's see what else I can cross out. I've got a half oxygen here and a half oxygen here. A half plus a half, carry the 1, yeah, that adds up to 1. So now I can cross out my oxygen because I have 1 on the product side, I have 1 on the reactant side. Looks like I'm ready to add up the entirety of my steps. So carbon plus H2O yields carbon monoxide plus hydrogen gas. So then I go and I check, does this match the target reaction that I was trying to achieve? It does. We're awesome. And now, in order to determine the enthalpy, or delta H of the target reaction, I now have to add up these terms, because we've manipulated them. We've changed the magnitude by flipping the sign. So this adds up to, I did it ahead of time, the delta H is equal to positive 132 kilojoules per mole. So this was a pretty simple and straightforward example. They get a bit tougher, but you just have to practice and get a feel for the reactions, and then you'll be able to solve your own Hess's Law problems. Thanks guys, we'll see you later for Bond Energies.